we want to be able to measure pressure. And when we measure pressure, there's something called a Burghardt tube. And what I encourage you to do is look at page 32, figure 2.9. My drawing in no way will be as good as that in terms of explaining what happens. But if I have my system, I'm going to have a system. Here's P of the system, so it's in here. And I want to be able to measure it. So what the Burghardt tube is it's really a curved tube that's hollow on the inside. And as the pressure changes, it causes it to flex. And then what happens is I have a little linkage mechanism at the tip of my finger, if you will, and that causes the gauge to move. And so if I look at this, I'm going to have something like this. And it has a variety of gearing. And then I'm going to have a pressure gauge. And I'm going to measure the pressure. So this measures P gauge. I also have out here P surroundings. And it's often P atmosphere, but not always. P atmosphere is 101.3 kPa. So we see that atmospheric pressure is 101.3 kilopascals. And so if the pressure inside the system were the same as atmospheric pressure, and that were the surrounding pressure, then P gauge would read 0. There's no gauge pressure. If the system is greater than that, then it causes it to deflect. Resisted by P atmosphere, it causes it to deflect. So if we look at this, then we see that P system is equal to P gauge plus P surroundings. So if I have then that P gauge is equal to 150 kPa gauge. And when you're measuring gauge pressure, you either put a G after it or a gauge after it so you know what it is. It's not absolute pressure. And the P surroundings is 100 kPa. Notice that's absolute pressure, and then P system is equal to 150 plus 100 is equal to 250 kPa. So I can determine the system pressure. Now let's look at another example where I could have a tank in a tank. So we could have a tank and a tank and a tank, but nonetheless, let's talk about that. There are some problems where we want to be able to describe this. And let's say that we have here, this is figure 210. And if I take a tank and I have another tank. So this is tank B, this is tank A, and we're going to have PA gauge. And we're going to have a pressure here, PB gauge. And so now, let's say that here, P surroundings is equal to 100 kPa. And let's say we say that PB gauge is equal to 120 kPa gauge, and PA gauge is equal to 140 kPa gauge. And we want to find PA. So we want to find that. So we know the surrounding pressure here, we know what this gauge reads, we know what this gauge reads, and we want to find out what this absolute pressure is. So now, I can find out what PB is. It's PB gauge plus surroundings is equal to 120 plus 100 is equal to 220 kPa. So now the 220 kPa, this is 220 kPa is the surrounding pressure on gauge A. So now I want to find out what the PA is. So PA is PA gauge plus P surroundings. So PA is equal to 140 plus 220. So PA is equal to 360 kPa. So you want to pay attention to what your gauge pressure is and what your system pressure is. So what we want to do is now look at just a diagram of how gauge pressure and absolute pressure relate. So if I look at this and I let this be pressure, and I'll have in here P atmosphere. So I have P atmosphere, and let's say that this is P. So now this is P absolute. So P absolute is from 0 to whatever P is. P gauge this is P gauge. And so it's like, this is what my gauge pressure is going, this is this. Oh, what happens if, how can I measure down? So now what happens, so the question is, this P gauge is what we call it when it's this way. What happens when I go this way? We're going to see what happens when P is less than P atmosphere. And we call this a vacuum. So if this is a positive gauge pressure, we could call it a negative gauge pressure, but that isn't what's used. Vacuum is what's used. Just like a vacuum cleaner creates a pressure lower than atmospheric, so atmospheric air pushes things into the vacuum cleaner. So it's something that you can tell your mother about because she normally vacuums, except in our household where that isn't true. And you can describe how it's working thermodynamically, and she may want you to demonstrate your knowledge besides just talking about it. So now let's look at this P vacuum. The atmosphere will have a pressure here P, and this remains P absolute. And this is P vacuum. So what I want to be able to do is to measure that, and to do that, we're going to introduce a manometer and talk about manometry. And so let's, I want to introduce that as well. And it has to do with the way the units on vacuum are measured. And so it makes sense if I introduce that in this case. So now with a manometer, the system, I have a manometer, which is a tube. And I'm going to have a liquid in here, and let me just have a liquid like this. And so if I look at this, and here I'm going to have P atmosphere. So P atmosphere is acting here, and if P sys equals P atmosphere, the levels are the same. So the levels are the same across. And so that's a characteristic of the fluid. Now, let's say that P system is greater than P atmosphere. So what's going to happen is the system pressure is going to push this down and we're going to get an imbalance. So now let me change this diagram, which fortunately I can do. So now I have this situation, and it's causing this to be. So now I want to be able to relate this height, L. I want to be able to relate the height L. It is going to have a certain density rho and acted upon by gravitational acceleration G. Let's look at what we want. I wanted to be able to relate this L and G. And so we have delta P is equal to rho LG. And so delta P we have, and so rho is kilograms per cubic meter. L is in meters. G is in meters per second squared. And so if I look at this, and this becomes a square, I have a kilogram meter per second squared. That's a Newton. So I have a Newton per square meter. So the units on this are newtons per square meter or a Pascal. So now if I divide it by 1,000, I have kPa. So delta P is equal to rho LG over 1,000 is kPa. Now, I'll leave this and we'll put some numbers in associated with it. Let L equal 0.5 meters. Let rho equal 13,600 kilograms per cubic meter. That's the density of mercury. So the density of mercury is very high. It's 13.6 times that of water. And we know that G is equal to 9.8. And so we want to, I can calculate delta P. Delta P is rho LG, which we just saw. So I have 13,600 times 0.5 times 9.8 divided by 1,000. And this is going to be equal to 66.6 kPa. And that represents the delta P difference between the system and the surroundings, which in our case we're going to call atmosphere. And so then P system is equal to delta P plus P atmosphere is equal to 66.6 plus 101.3, and that's going to give me 167.9 kPa. So I can use this, I can use the manometer to measure pressure, and I basically am going to look at L in being able to do that. And now, we do this, and actually for positive pressures, sometimes we do it for furnaces and things like that, so there's a positive air pressure in there, and you'd be measuring the delta P based on inches of water. So when you're using fans and things like that, you might be measuring in inches of water, and it'd be a positive pressure. When we're measuring vacuum, we're going to be measuring it in millimeters, typically millimeters of mercury vacuum, and we'll be looking at that. So now, let's change things around and look at what we have if I'm measuring vacuum. So I'll change this dynamic. So now we're going to have a vacuum. So if it's a vacuum, it's less than atmospheric, so I'm going to have P atmosphere here. And what P atmosphere is doing is pushing this down, so now L will be this way. And we'll use the same values that I had before, but now we're measuring what the P system is. And so we'll have L is 0.5 meters, which is 500 millimeters, just to Hg, just so we get used to that. Rho is 13,600 kilograms per cubic meter. G is 9.8. I know that delta P is equal to, excuse me, 66.6 kPa. We already did I just did that calculation, so we don't have to do the calculation again. And now, P system, and I want to talk about something that I call the swim-through method of determining pressure. So we'll do a swim-through. And I could let this be a. And what I'm interested in is P system. And what I know P atmosphere. So I know P atmosphere. So if I were to start at B, start at B, and there I have P atmosphere. P is equal to P atmosphere. So I'm at B. I then pretend I'm going down. If I go down in a pool, the pressure increases. So if I go down, it's a plus delta P. If I go up, it's a minus delta P. So I'm going down, it decreases. I come up to A, and it's the same as B. And so now I'm over at A, and PA equals PB, which is equal to P atmosphere. So now I'm at PA, and I'm going up. So what's going to happen to the pressure? Is it increasing or decreasing? Is the delta P increasing or decreasing? It's decreasing because I'm going up. So I have PA minus delta P. And now where am I? I'm at P system equals P system. So I have PA is P atmosphere, 101.3, minus the delta P, 66.6, and that's going to give me 34.7 kPa. And so this is a swim-through technique. I could do it starting here. If I did it here at P system, I would be going down, 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 and I'd have plus delta P, and then I'd come over here to PB, which is P atmosphere. And so that's what we have. So now the question, so this is with a vacuum pressure, how low can you go? I can go to 0. So what is the value of L if the pressure is 0? If P sys equals 0 kPa. If I look at this, then I have delta P, which is equal to P atmosphere minus P sys, is equal to rho Lg over 1,000. So if I have that, P sys is 0, right? That's 0. So now I have 101.3 is equal to 13,600 times L times 9.8 divided by 1,000. And we solve this, and we see that L is equal to 0.76 meters of Hg, or 760 millimeters Hg.